this chapter, we're going to introduce the simplex method. Okay, so simplex method is a very general procedure for solving linear programming problems, and it has proved to be remarkably efficient and used routinely to solve huge problems on computers. Moreover, extensions and variations of the simplex method has been used to perform post-optimality analysis, such as sensitive analysis, as we'll see later on models. So we start by introducing the geometric interpretation of the simplex method. Given an LP problem and its feasible region, we first can find its counterpoint solutions, or CPF solutions in short. This by name means just the corners of the region. Then what the simplex method does is to check whether a CPF solution is an optimal solution or not. The way of checking this procedure is called the optimality test. We say if a CPF solution has no adjacent CPF solutions that perform better, and by better here we mean is measured by our objective function z. If nothing performs better than that CPF solution, then we say this CPF solution must be an optimal solution. So this is the optimality test. Now let's look at an example how this idea works. Consider the example of maximizing z equals 3x1 plus 5x2 with all these constraints. So first, geometrically, we'd like to draw its feasible region. And moreover, since we mentioned earlier, the simplex method uses CPF points, we can list out all these counterpoints of the feasible region. And then for each counterpoint, it has two adjacent points. We can list out one counterpoint and all its neighbors here. Then the simplex method says we start at one corner, at one CPF solution, and then repeatedly apply the optimality test. Then the question first is, well, to start. Of course, by looking at this picture, the most general and easiest one to start with is the origin. So we choose the origin 0, 0 as our initial CPF solution. At this point, of course, we need to check our objective function at that point is 0, since both x1 and x2 are zeros. Next, during the simplex method, we check whether the adjacent points of the origin perform better. So the origin has two adjacent CPF solutions, 0, 6, and 4, 0. We substitute their values in our objective function, and we find out that at 0, 6, the objective function is 30, and at 4, 0, the objective function is 12. Both are better than the original 0. So this tells us the 0, 0 is not our optimal solution because its neighbors perform better. So then we go to the iteration. We change from 0, 0 to the next better CPF solution. And of course, among 0, 6 and 4, 0, 30 is a better one. So we change from 0, 0 to 0, 6. This is the next CPF solution. At each CPF solution, we repeat the same procedure. 0, 6 has two neighbors. One is 0, 0, which we checked. It doesn't perform better. And the other is the 2, 6. So we check the neighbor 2, 6, whether that performs better in z. So after substituting x1 equals 2, x2 equals 6, we see the objective function at that point is 36. That is definitely better than 30 at 0, 6. So this says 0, 6 is not an optimal solution, and we move to the next one, which is 2, 6. And then we repeat the same procedure. 2, 6 has two neighbors. One is 0, 6, which we checked earlier. The other is 4, 3. However, when we substitute 4, 3 to our objective function, we can also check this is not better than 36. So at this point, the CPF solution 2, 6 has two adjacent CPF solutions, but neither of them perform better than the original one. So this tells us the simplex method terminates, and it says if no neighbors perform better, then this CPF solution is actually our optimal solution. So this is the procedure geometrically how the simplex method works. It simply checks, start from one corner and checks all the neighbors and see whether the neighbor performs better. If yes, then move on. If no, we stop. So from this procedure, we can first see some insights and key concepts of the simplex method. First, we say the simplex method focuses only on CPF solutions. For any problem with at least one optimal solution, finding one requires only finding a best CPF solution, as long as our feasible region is bounded, which we will see more details later. Next, we say the simplex method is actually an iterative algorithm. Its flow, as we saw, is actually as follows. We first set up the model and then start the iteration by finding an initial CPF solution. And then we do the optimality test. Is the current CPF solution optimal? If yes, then that's the optimal solution. If no, then we perform an iteration by checking its adjacent points to find a better CPF solution and repeat the optimality test until we stop. Third, we say to start the simplex method, we need an initial CPF solution. And the most general and easiest one to choose from is always the origin, while all the decision variables are set to be 0. Fourth, we say given the CPF solution, it's actually much easier computationally to gather information about its adjacent CPF solutions than about other CPF solutions. Therefore, each time the simplex method performs an iteration, it always chooses a CPF solution that is adjacent to the current one. Consequently, as we can check with the previous example, the entire path followed to eventually reach an optimal solution is actually along the edges of the feasible region. Next, we say after the current CPF solution is identified, the simplex method simply identifies the rate of the improvement in Z that would be obtained by moving along the edge. Then it chooses to move along the one with the largest rate of improvement in Z, hoping to reach our optimal solution faster. Last, we say the optimality test consists simply of checking whether any of the edges give a positive rate of improvement in Z. If none does, then the current CPF solution is optimal. So the next time, we're going to talk about the algebraic interpretation of the simplex method. Without pictures, how do we actually solve a linear programming problem?